Hi guys, in today's video we're going to be looking at the conservation of mechanical energy. So this is going to be a general physical principle which is going to help us save us a lot of time when we try to solve dynamics problems. So it's very important to understand all of the concepts here, because if you sort of understand this basic general principle, you can apply it and you can solve these problems very efficiently and very directly. And so in today's case, you'll even see a scenario where using Newtonian mechanics to solve the problem is not very straightforward. It's not very obvious how to do that, but energy considerations make our lives much simpler. So the idea here today is that we just want to look at our initial mechanical energy, which is defined as our kinetic plus our potential. And we just want to say that that total initial mechanical energy has to be the same at all times. So that's to say at any given time, so we'll call that the final time, our initial mechanical energy is equal to our final mechanical energy. So we say that this quantity, the mechanical energy, is conserved, meaning that it stays the same at any given time. So this is really this general principle, and there's not much more to it for this chapter. This is only true in the case where there's conservative forces acting, but today we're going to be only concerned with the force of gravity, which will be a conservative force. And so we dealt with in the last video non-conservative forces, so you should look back to that video if you want an idea of how to deal with non-conservative forces. But assuming our mechanical energy is conserved, we have conservative forces, this is really all we need. And so the only other thing we need to remember is that the gravitational potential here is mgh, and then the kinetic energy is going to be 1/2 mv squared. Okay, so let's look at the problem statement for today, and that reads as follows. A car in an amusement park ride rolls without friction around the track shown in the figure below. It starts from rest at point A at a height h above the bottom of the loop. Treat the car as a particle, and we want to know what is the minimum value of h in terms of r, such that the car moves around the loop without falling off at the top. And then B, we want to know if h is equal to 3.5 r and radius is equal to 20 meters, compute the speed, radial acceleration, and tangential acceleration of the passengers when the car is at point C. At this point, you should pause the video, reread this problem a couple times, and maybe even try it on your own. Okay, so we have our scenario drawn out over here. So we see we have the car, starts up here at point A, and then it sort of rounds this loop, and here B is the top of the motion, C is over here. So we'll look at point C later, but to start we want to look at point B, which is to say when the car is at the top of the loop, and we're asked to solve for the height h such that the car just barely makes it around this loop. So we see we're going to have some circular motion, so we'll have to be worried about radial forces, and then we're also going to want to use energy conservation here because we're going to start with some potential energy, and we'll see how that'll sort of transform into kinetic and potential as well. So the first step here is going to be to just draw the free body diagram at point B. So for that case, we have the particle is right here. We know, of course, we have some force of gravity on our car. And then the other force that we have here could be our force normal. Right? The top of this ramp is going to be pushing down on the car in general in order to keep the car from traveling through the ramp. So these are sort of our two forces in our free body diagram. And so this is our first step. And so these two forces are actually acting on the car. And then we want to also remember that we know in order for there to be circular motion, which is the condition that we want, we're told we want it to keep traveling around in this loop, we need there to be some radial force pointing towards the center of the circle, which in this case is straight down. And we need that to have a form F radial must be equal to mv squared over r. So if it's not of this form, we're not going to continue to have uniform circular motion, or circular motion at all for that matter, and therefore we would not have a scenario where this car is going to keep going around the track. So this is sort of our condition that we know needs to be true. And so of course we also know that F radial is going to have to just be equal to the sum of the forces that are acting towards the center. So in this case, the two forces, Fg and F normal, are both acting towards the center. So basically we're saying we want these two forces added together to give us our mv squared over r condition. So we can sort of rewrite that below as Fg plus Fn should be equal to mv squared over r in order for there to be circular motion. So this is our condition. And now we need to think about what the question is actually asking us. So it's not just asking us this, which is going to be in general could be true. What it's going to ask us is asking us the minimum height such that this will just barely be able to satisfy this condition. So that means that we want to start by thinking of how is changing the height going to affect some quantities that we have in this equation here. Right? And so we see a quantity we have in this equation here is velocity. And I think it's pretty clear that if the height that the car starts at is lower, it has a lower initial potential energy, and therefore it's going to be able to have less velocity at the top of the loop, if it can reach the top of the loop, of course. So basically, the smaller the height, the lower the velocity that the car is going to have at point B. So when we ask for the minimum height where this is allowed to go around in a circle, what we're really going to be looking for is the minimum velocity. Right? The height and the velocity are directly related, so the question is going to also amount to a minimum velocity. So I'm going to start from there and we'll work backwards. But if we want to get our minimum velocity here, we want to look at this condition. And the first thing that we need to note, and this is something you need to make sure that makes total sense to you because this is a very important step, is to note that this normal force can be sort of whatever it needs to be in order to keep this condition true, as long as it is greater than or equal to 0. So our normal force, if let's say our car is going much faster at the top, we drop it from a way higher distance than normal, our car is going to be going faster than it would have been, and therefore our normal force needs to step in order to apply that greater radial force that is required with the greater velocity. So our normal force is basically going to step in to just give us the extra force that we need to keep the car traveling in uniform circular motion at the top of this track. And so that'll just depend on the velocity here. And so basically the minimum value that our normal force could be at would be equal to 0. And so that would be the case where we only have the gravitational force acting as our radial force, and we don't actually need any extra normal force because the velocity is so small. And so our normal force, basically, we just need to see that this will just change based on the velocity. So if we want the minimum velocity, we want the scenario where F normal is going to be equal to 0. So we want this to be true. And of course, Fg is going to be constant no matter what we do. So this is going to be the minimum total radial force we can have is Fg. And that means that will give us our minimum velocity, would just be Fg equals mv squared over r. And we can sort of solve from there. So if we plug this in, if we sort of cancel this out as 0, we can get that our minimum velocity should be equal to the square root of gr. So I've just plugged in mg for f, the m's cancel, and we can move things around. And we get this, which is a very important step, which is to say our minimum velocity at the top of the ramp is going to be the square root of g times r. So at this point, we know our velocity, and we know that the height and the velocity should be directly related. So really all that's left is to apply our mechanical energy conservation. Instead of trying to worry about every force that's acting on this angled ramp, we can just go ahead and say we know that this starts with some mgh. It starts with a potential energy. It starts from rest, so this is the only total mechanical energy is just going to be equal to mgh initially. And that must be equal to our mechanical energy final, which will be equal to, and I'll explain this in a second, will be equal to mg2r plus 1/2 mv min squared. And this is to say this will solve us for h min. So this mg2r comes from the fact that at point B we also have some gravitational potential. We'll set sort of this ground to be our 0 point. So then h min is from that ground, but we see at the top of the ramp we are 2 radiuses above the ground. So this is just mg times h, which is 2r. So again, this is our condition for our minimum height, minimum velocity, and we can solve this directly, and we should be able to get an answer that h min is equal to 5/2 times r. And so that is the condition that we will be concerned with. H min is 5/2 r. Anything below 5/2 r, and our radial force, Fg, is going to be too big to keep our circular motion, and this ball will sort of just fall to the ground. This car will fall to the ground. So this is part A. So now let's switch colors to talk about part B. And so for part B, we were asked, at point C, we're given some height, which was 3.5 r. So they tell us we have a height of 3.5 r, and they give us the value of our r, and the value of our r is 20 meters. And they say, given these parameters, what is the radial acceleration and tangential acceleration at point C. So this is going to basically just, we can get this straight from our energy conservation. So we know our initial energy is again just the mgh. So we just have m times g times 3.5 r. And this is our total initial mechanical energy. And then our final mechanical energy, we see we are a distance radius above the ground. So we have mg times radius. That's our gravitational potential energy. And then to that, we want to add, of course, whatever our velocity is here. So that would be 1/2 m, I'll call it vc. To recall, this is just the velocity it's going to have at c. We're not worried about minimum anymore. We're just worried about the velocity it has given this height. So that will just be vc squared. And so then in order to find what we're asked for, which is the radial acceleration, we just recall that is of the form, sorry, there's no m here. This is not a force. So that is just of the form v squared over r. So if we can solve this for v, plug that into our equation, we should be able to get a radial acceleration. So I'll let you guys do that at home. First thing to note, though, of course, is these m's cancel, which is good because we don't know the mass and we don't need it. So if we plug all of this in and then plug it in for the velocity, we should get a radial acceleration of 490 meters per second squared. So that's to say, at this point, this will be our radial acceleration. And so then it asks us also for an extra piece of information, which is we want to know the tangential acceleration as well. So in order to find that, let's go ahead and draw over here our free body diagram. And so from our free body diagram, we see that we will have some normal force from the ramp right here pushing inwards. And so in this case, that is the radial force. So let's recall this is radial force. Towards the center is to the right here. This is point C. And the only other force acting is just the force of gravity pulling downwards. So if we just look at this, we actually see that the forces acting at point C are very special in that they are directly aligned with our radial and our tangential force already. So our normal force is the only thing that is our radial force. That's going to give us this acceleration. And so the only thing that's going to give us a tangential acceleration is gravity. So we can just say right away, this is telling us that our tangential acceleration must just be equal to the magnitude of gravity. And so if we want to worry about our directions, of course, this should be 9.8 meters per second squared pointing downwards, and this should be 490 meters per second squared pointing towards the right. So however you want to define your coordinate system, that may be positive or negative, but the direction itself is more important. This is down, that's to the right. Okay, so let's review how we just did that problem. We first drew our free body diagram and noted that we had a requirement that the sum of the forces pointing towards the center of the circle be equal to mv squared over r in order for there to be circular motion. So then we set the normal force equal to 0 to find the minimum velocity, and we used mechanical energy conservation to solve through to find the minimum height. And then for part B, we drew our free body diagram and again utilized mechanical energy conservation to solve for the velocity of the car at point C. And then we plugged this into our radial acceleration equation and got an answer, and then noted that the tangential acceleration was just equal to g. Okay, so I hope you guys found this video useful, and you sort of see now the utility of using energy conservation in these dynamics problems. So please leave any comments you have about this video or any of these videos on TED. There should be a link to the right of the video links. Thanks for watching.